Hello everyone. So today I want to talk about one of the most important reaction types in organic chemistry. It is enolate, guys. These all the reactions here, 5 reactions I'm going to talk about. They have something to do with enolates. So of course, the first step of all of these 5 reactions, they're going to start with enolate formation. So what's an enolate? An enolate is of course your anion, which looks like this. This is the enolate, which is a conjugate base of the enol. This is what you call an enol. And to form an enolate, you will need a ketone with an alpha hydrogen, meaning a hydrogen at the alpha position, which is this one. So this carbon is the alpha carbon, because it's next to the ketone or the functional group that we're interested in, which is the ketone in this example. And it is quite acidic. Why is that? Because it is next to an electron withdrawing group, which is the ketone, the carbonyl. Plus, after extraction of this proton, it can resonance into the carbonyl. So let's say I have a base, maybe LDA, some kind of an alkoxide, whatever. A base will, of course, grab this proton, just the base always does. And this CH bond, let me get rid of this. And the CH bond right here will come here, kicking the electron up to the oxygen. Here it is. This is your enolate, right? And it can and it has a resonance structure. So this is one of its, or only resonance structure actually. So this will be its resonance structure. So now the negative charge is on the carbon. So now we know 2 things. One is that the enolate is relatively stable. It's not the most stable. It's not the most stable thing in the world, but it has a resonance structure. The acidic proton right here is quite acidic. The proton next to it, so it can be abstracted. And the second thing is that the resonance structure indicates right here is that the negative charge is on the carbon, meaning to say that this carbon bears a bit of a negative charge. So it has some nucleophilicity on this carbon, right? Because this carbon has a negative charge. So now we can use this knowledge to do some interesting stuff, like build some carbon-carbon bonds. Because let's say, okay, we know that this carbon is nucleophilic. What if we introduce it to an electrophile? So it's going to do a reaction together, right? Nucleophile and electrophile. Depends on the electrophile. Maybe it could be an attack on the carbonyl, on the other carbonyl, or an SN2, right? If it's an alkyl halide. So, for example, the Aldol reaction is a reaction with your ketone, which has been turned into an enolate, maybe with LDA. That's a base, quite a bulky one. This is my enolate. And with another ketone or another aldehyde up to the starting materials that you've been given. Let's say it's an aldehyde with an R group right here. Let's say that this is my electrophile. So I have my nucleophile ready. It's in the form of the enolate now. So what's going to do is that the oxygen will form the double bond back, kicking this double bond to the carbonyl. Here's an attack on the carbonyl, and kicking the CO double bond. So you will get this product. Our group right here. Oh, maybe with a proton exchange. So it's going to look like this. Great. Now we have this product. Now what can we do further is that we can further maybe give it a bit more base, even more base. which is not really explicitly written, but maybe it will be written as heat, is that we can give it some heat to let the base grab this proton once again. So in this case, you have a base, grab this proton once again, and once again it forms the enolate. So now you have your enolate back, and you can kick off the alcohol, the hydroxyl group right there, to form an alpha beta conjugated carbonyl. This is quite a very interesting, not really interesting, but very useful kind of carbonyl, an alpha beta conjugated dehydrated, right? It's called alpha beta unsaturated ketone. This is a very important things a compound can have, because it can undergo a Michael reaction, which we will talk about it later. So in general scheme, if I have, so in general, let me draw a scheme. So in general, if I have a ketone with one LDA and an aldehyde, it's going to form something like this through the mechanism above. And if you give it some heat, same thing, LDA, but in this time you're going to mix it in one pot. So it's going to be LDA and then I drew a ketone, not an aldehyde. This one's going to have another methyl group. So I'm just going to change it into a hydrogen then, so that there will be any confusions. Hydrogen. Okay. So let's say I have LDA and I treat it with this aldehyde, and then I also add some heat onto the system. It's going to form an alpha beta unsaturated ketone, like so. So that's going to be your general scheme. So if there's no heat added, you can assume that it's going to be a beta hydroxycarbonyl. But if you have heat added, it's probably more on the unsaturated ketone side. So there you go. Claisen is, so next is the Claisen. Claisen is similar to Aldol in a way that you also attack the carbonyl. So let's say I have a ketone again, and LDA. So that, of course, will form your enolate. And what's special about Claisen is that we use an ester instead of an aldehyde or a ketone. So let's say I have a methyl ester instead of the aldehyde. Then same thing happens. So you will form a tetrahedral intermediate. So it's going to form like this. Now how do I draw this to make it look beautiful? To make it look nice. Anyways, here you go. This will be your intermediate, right? Then what's going to happen next is similar to when you do acyl substitution, right? But instead of water or nitrogen or an amine as your nucleophile, you have an enolate as a nucleophile. So what's going to happen is that the CO double bond will reform, kicking out the methoxide. So it's going to be this product. Sorry. Let me translate that into a more beautiful product. 1, 2. Right? There. Yeah, okay, here you go. This is the product. This is the Claisen condensation, right? I think it's called the Claisen condensation. It's similar to an aldol, but instead of your aldehyde or ketone, you use an ester. And actually, you can also have an ester as an enolate also. Let's say I have an ethyl ester treated with aldehyde. Same thing's going to happen, is that it's going to form an enolate, but using an ester this time. And it can do the same chemistry, just like what we just did above. So it can go attack something else, it can go attack itself, it can go attack, whatever. It can also do the same thing. Now, Dieckmann cyclization, right? Cyclization, whatever. It's just Claisen, but intramolecular Claisen. It's just a fancy name. It's intramolecular Claisen. So let's say I have this compound. It's gonna take a while to draw. Maybe here. Okay, let's see. Let's say I have this compound, and I treat it with a big base, a bulky base. For example, let me give a new one, LiHMDS. That's a big base. So the bulky base will abstract the least sterically hindered proton, and in this case it's going to be this red proton over here that's going to be abstracted. Can it abstract this proton on the other side? Well, it's going to have a harder time getting into it, because LiHMDS is quite a big base. If you want to know what it's like, it looks like this. This is the HMDS part, and the lithium part is just the counter ion. This is LiHMDS. As you can see, it's quite big. So abstraction at this position is quite unlikely. So it's going to abstract proton at that position. So now I will have an enolate right there. Now, one thing to note is that Claisen or Dieckmann, it doesn't have to be a ketone and an ester. It can also be an ester with an ester, but it at least need to have at least one ester. So it's going to be a tetrahedral intermediate. Now let me draw the shorthand version. There you go. And you will form a 5-membered ring with a dicarbonyl, like so, and a 1,3 dicarbonyl. Now, what's interesting to note right here is that with an aldol reaction without condensation, just aldol condensation without condensation. Maybe I should say aldol reaction, maybe. With an aldol reaction, you can see that this is a 1,3. This carbonyl and this hydroxyl group has a 1,3 relationship to each other, right? It has a 1,3 relationship. So it's going to be 1,3. So is Claisen a 1,3 diketo, right? It's 1,3 related to each other again. Dieckmann is just Claisen, so you would expect it to be a 1,3 diketone. But for the next reaction, which is the Michael reaction, it will be a 1,5 diketone. So first step is, of course, the same thing, which is enolate formation. Let's say that we have the same ketone, which is acetone, and with aldehyde or whatever forms the enolate. Now, as I said, alpha-beta unsaturated carbonyls are important because they can undergo microreaction, and this is what it's going to do. Let's say I have the ketone from that I made from aldol. This is the ketone. Thing that you need to know here is this carbon that I marked it in red is electrophilic. It is really electrophilic, and it's going to be so susceptible for an attack with enolate chemistry. So an enolate will love to attack here so much. It will really want to go here, attack here. Why? Because one, this double bond can resonate into the carbonyl, as you will see right now. So there's an attack. And now a new enolate has been formed. Right here, right? Okay. And then after this enolate will go grab maybe a proton from water to get your micro addition product. Here we go. This is the microreaction. And it also has a fancy name for the components involved in microreaction. So the enolate, that is the nucleophile, is called the Michael donor. And the electrophile that's been attacked is called the Michael acceptor. Great. That is the microreaction, and this is just, as I said, this is a 1,5 diketone. It has a 1,5 position related to each other, so 1, 2, 3, 4, 5. Great. Now the last reaction is called the Robinson annulation. So let me just add annulation right here. Now to annulate means to close a ring. So it's kind of like to Dieckmann. It's also not, because Robinson is Aldol. And sorry, Michael comes first. It's Michael plus Aldol. And it gets another fancy name, which is Robinson. So for this reaction, a new ring has to form. As the name suggests, annulation. So there's going to be 2 steps involved, which is Michael and Aldol, just like I said. So let's say I have a diketone right here. This is a very common example, so I'm going to use it. Let's say I have this one right here. First, I treat it with LDA. No, it's too bulky. Let's try something else. Let's try sodium ethoxide. So that's going to abstract the most acidic proton, which is this proton, because it's sitting right in the middle of 2 carbonyls, so it's going to be the most acidic, as you expect. So it's going to look something like this. The enolate, this is the enolate. So let me draw the mechanism of the abstraction, proton abstraction. There you go. Then I'm going to introduce a Michael acceptor. Commonly is acrolein, right? I think this is called acrolein. I think so. Well, sometimes aldehyde can be too electrophilic, so I'm just going to add another methyl group to make it selective. Because sometimes conjugated carbonyls, if it's an aldehyde, it can react at the aldehyde carbon, because aldehydes are more reactive than carbonyls, right? So I'm going to change it into a ketone, to make it more selective for the conjugate addition. This method of attack is called conjugate addition, by the way. Conjugate addition. Like so. The arrows look really fancy. I love it. So now you will have this and the newly formed, not newly formed, but newly attacked carbonyl by itself. Good. Now what's going to happen next is that I'm going to drop a base, LDA, and it's going to abstract this proton. Now I chose a bulky base because it's going to abstract the least sterically hindered proton. So it's going to abstract here, or maybe I'm going to draw an arrow out of the base. It forms an enolate once again. Going to put it down like so. Okay, here's my enolate. And it's going to attack this so hard to draw. Ketone. It's going to attack this ketone. Going to check my ring. That's a 6-membered ring, so I'm going to draw a 6-membered ring. Going to draw a 6-membered ring. There you go. The OH comes out of here, and then the carbonyl comes out here. Same thing is going to happen, similar to what happened in Aldol condensation, is that we're going to add some heat. And the base is going to abstract this proton, forms the enolate once again, and then it's going to kick out the hydroxyl group. Like so. And it's going to be your final product here. Boom. Which is also a conjugated enone ketone. So that's why you call it enone. Well, there you have it. These are the most important reactions in alpha beta chemistry. And yeah. Goodbye. Thank you for watching.